Hi there. We are Group C, and our project is called the ADEPT, or Analog and Digital Effects Processing Technology. What is the ADEPT? Our project is an open source digital audio effects processing solution designed with engineers in mind. It's an effects pedal that can be used with any instrument with a standard 1/4-inch instrument cable output. In the past, there have been other senior design projects pertaining to music and audio processing. However, our project stands out in a few unique ways. While other projects have utilized rack mount systems, large enclosures, or even multiple enclosures, our project will be housed within a robust, compact foot pedal layout, standard to most musicians' pedal boards. Our audio effects are fully digital, with the volume and tone controls being provided by simple analog circuitry. We also have a user-friendly interface that allows for a simplified control scheme that is bright and visible even under low light conditions. We have also chosen to make our project open source such that anybody with some coding and soldering experience can assemble it on their own, or even modify the design to their own needs. We believe this will be a good learning experience for those with an interest in embedded systems, electronics, and music. For our demonstration, we will be outlining several of the engineering requirements we initially set out to achieve at the start of Senior Design 1. These include analog to digital conversion using our PCM3060 codec, demonstrating a high input impedance and low output impedance, standard 1/4-inch instrument cable compatibility, 9-volt 500 milliamp DC power, serial wire debug programmability, LCD menu and selection screen utilizing potentiometers and a rotary encoder, and a dual foot switch functionality with an on-off switch and a tap tempo and looper switch. While we still have a while to go, we feel that we have made great progress thus far. Let's begin with an overview of our current PCB design. Here's our current PCB design, created using Autodesk Eagle. Here's our PCB, as well as some changes that we have made in the past few weeks to our design. This is our first version of our PCB. As you can see, we have fully populated it and gotten it to turn on. All of our voltages work properly at 5-volt supply, 3.3-volt supply. We are able to interface with the MCU, as well as create a heartbeat LED test program. All of our potentiometers work properly. The only things we had to make some edits to were this LCD screen contrast, as well as the actual backlight for the LCD screen. We're not previously connected. We also have yet to connect certain pins on the rotary encoder switch for the menu selection. And in addition, we have yet to make some edits to our ADC DAC codec, as well as our flash memory, which have some pins that have not been configured properly. In the meantime, we are using this breadboard system with an STM32 Nucleo development board, and all of our essential block diagram elements of our design, with this being the input buffer, output buffer, volume and tone stages. We also are utilizing a flash memory breakout board, as well as a codec breakout board, which is not currently present. We are able to run a guitar signal all the way from the beginning to the end of our breadboard layout. The codec, as you can see in our demonstration, does pass a full guitar signal. We only have yet to implement reading values from our codec, as well as implementing effects processing within the MCU. For our project's enclosure, we initially decided to go with a 1590 BB standard double wide guitar pedal enclosure size. We later learned after ordering these enclosures that our PCB was going to be a bit too large to fit in both the components as well as the PCB itself. So because of this reason, we decided to go with a little bit of a larger enclosure, which should most certainly meet our needs. Here we are performing a test where we are plugging in our DC power supply and seeing how our voltage regulators have reacted with their transient response. In the yellow is the 9 volt, green is 5 volt, and blue is the 3.3 volt. We did the same with unplugging, just to make sure we were getting a clean response. Here we're demonstrating that we have a high input impedance and a low output impedance according to our requirements. Here we are performing a breadboard test of our volume and tone controls. We are sending in a square wave input, and here you can see me adjusting the amplitude of our square wave by turning the volume knob. And here we're adjusting the tone knob, which is just a first order low pass filter. In the clip that follows this, we'll be performing a practical demonstration using a guitar looper pedal with a constant loop running in the background while I adjust the volume and tone. Here we are going to test our LCD menu with our parameter potentiometers and our rotary encoder. So here I'm going to change from one effect to the next using the rotary encoder, and I can use the parameter potentiometers to change any of our values between 0 and 99. By implementing a 10 kilo ohm trim pot at the input to our contrast pin of our LCD screen, we're able to adjust the brightness of the characters and therefore the contrast of the display. Here we are performing a simple tap tempo switch logic test, so as you can see, every single time I hit the switch, the LED will turn on. So here we have our guitar hooked up to our input buffer, which is hooked up to an oscilloscope. We are performing this test in order to see what the amplitude range of our guitar is. And this is important for the input to the codec, which will provide our analog to digital conversion. We need to make sure that we don't need to provide a DC offset or to amplify our input voltage from the guitar at all. And here it seems that we have a perfectly suitable range for the input to the codec. In order to confirm the functionality of the DAC as well as the ADC of our codec, we connected the data in and data out pins of the codec, which essentially just creates a loop, and we were able to run a simple sine wave all the way from input to output with no processing. In the next clip, we tested out how this sounds using the guitar as an input, and as you'll be able to hear, there is a little bit of digital noise in the signal. However, this was later mitigated by utilizing low-value resistors across the I2C and I2S lines to minimize reflections. Here we are measuring some of the I2C lines of the codec. In purple is the incoming data, and in blue is the BCK, or bit clock. With some simple math, we're able to take our period of 325 nanoseconds between each rising edge of the bit clock and confirm that we are indeed sampling at 48 kilohertz with an input clock frequency of 12.288 megahertz. And here you can see in purple the incoming bit data as well as the left and right channel framing of the LR clock in blue.
There we go. Sweet. There we go. There we go. Perfect.